Let me show you a little bit of NMR. So let's say that we have CH4, standard organic compound. What would be the NMR of CH4? Why? I have 4 hydrogens. But they are all equivalent, right? So I will have just 1 peak for hydrogen. How many peaks will I have for BH4? First of all,
what range are we in? Are we looking at the boron or are we looking at the hydrogen?
Excellent question.
Okay.
Proton NMR. Well, at least one. At least one, right? The problem is, in this case, different than carbon. Carbon 12 doesn't have a nuclear spin. But in the case of boron, boron does have a nuclear spin. Where is the nuclear spin of boron?
Depends on the isotope.
Boron 3, boron 11. 3 halves, right? So, and now it's all the sigma mi, which is the splitting. The splitting of any atom is going to be equal to 2I n plus 1. I'm just going to do the demonstration. 2 times the spin of the species that is coupling, which is boron 3 half. How many boron 3 half there are? 1 plus 1, so that means 3 plus 1 means 4. The hydrogens are all the same, so my proton NMR spectrum is going to be a beautiful quartet, and the intensity of those bands will be exactly the same. If you have to report the chemical shift, it will be exactly between those two. Are you confused? What if I enrich my methane and all my methane is now carbon 13? What will be my proton sigma, my proton NMR? A doublet. In an enriched sample of carbon 13, methane will be a doublet. And in a real sample of of methane that has what is the abundance of carbon 13? Is it here?
1.1%.
1.1%, right? So in a real sample of methane, you probably will never notice it, but you will have your singlet and here at 1% you will have something like this. Those are what we call the satellite bands, and they're due to the carbon-13 that is present in the sample. Probably you will never see it because it's below 1%, but it's there.
So this one is for the carbon and this one is for the hydrogen?
No, this is for standard CH4.
Oh.
This is for enriched CH4 with carbon. The thing is that normal CH4 will have 99% of this and 1%. Are you with me? Because now, if yes.
So that means that for 13CH4, would you get a? Oh wait, no, you wouldn't get a small spike from C12.
Answer.
Because so for the normal CH4, you showed us that you get a small 13C spike, right?
Mm-hmm.
So I was going to say that does that mean that you will does that mean that you will see a small 12C spike, but you won't because there's
No, exactly. And this is 100%. I'm saying enriched 100% C13. Okay, now what happens if I ask you to do the boron 3½ NMR? Boron 3½ NMR. What's going to happen? How many different borons do I have?
Hopefully not more than one.
Only one. But what's going to happen to that boron? Is it as isolated? It is not isolated. It is what? What does it feel? The field from the hydrogens. There's a magnetic field from the NMR detector, but then the hydrogens around this boron are coupling parallel or anti-parallel to that magnetic field. So that's going to change the energy of the transition of boron, depending of the orientation of those hydrogens. So how many orientations those hydrogens are going to have? Well, I can have them all parallel. So they can have all 1/2 speeds, right? The sigma mi there will be 2. And how many ways I have to organize this? How many permutations can I have?
One.
One. Of course, a population will have that, but then a population will always also have most of them facing the magnetic field, but one facing the other direction. The sigma mi there will be 1. And how many ways? One way. How many ways, how many permutations I have for that? 4. Let me see, 1, 2, 3, yes, 4 ways. Do you see it? I can have that. I can have, I'm going to write it below, but then I'm going to erase it. I can have that. I can have 1/2, 1/2, minus 1/2, 1/2. I can have 1/2, minus 1/2, 1/2, 1/2. And I can have minus 1/2, 1/2, 1/2, 1/2. I have 4 different ways in which I can order that. Right? 4 different combinations. Alright. Another one. I can have how many ways I can order that? I can rearrange that. 6 ways. Do I need to do it or can you see it? Then the other 2 possibilities are very straightforward. So we can have minus 1/2, minus 1/2, minus 1/2, and 1/2 positive. This will be minus 1, and there will be 4 ways. And then we can have minus 1/2, minus 1/2, minus 1/2, minus 1/2. This will be minus 2, and there will be
1.
very good. So, how many boron signals are going to have? 5. 1, 2, 3, 4, 5. Due to the different orientations that my spins can have. I have 5 different orientations. If you don't believe me, then you can go to the splitting formula. 2in plus 1, 2 times 1/2, because now the things that split are the hydrogen atoms, times 4 plus 1, that makes 4 plus 1 equal to 5. The splitting formula tells you how many lines you're going to have, but it doesn't tell you what will be the abundance. So in this case,
There's a 1, 4, 6, 4, 1 pattern.
yes, my splitting will be 1, 4, 6, 4. Of course, you didn't need to do this, because I can tell you right now that every time that nuclei with spin of 1/2 are splitting, then you can use something that you use in organic chemistry a lot, that is called the Pascal triangle. So, if and only if the nucleus or the nuclei that are splitting have a spin of 1/2, then you can use the Pascal triangle to determine the split. Are you with me? Can we make it harder?
Let's.
What is the boron? No. Let's make the molecule. And actually, I'm gonna put here an alkene just for the sake of not having any splitting. So actually, I'm just gonna put here R groups, just not to complicate too much the molecule. R groups, they are quaternary carbons. They are all carbon 12. They don't couple with anything. So yes.
So in the previous example, you were doing the sigma MI. What's that? Like your 2, 1, 0.
That's the total spin. You don't.
All.
That's the total spin. So if I have 1/2 plus 1/2 plus 1/2 plus 1/2, the sigma mi is 2.
And is that the same as the 2 ion plus 1?
No.
That is also.
No. That the 2in plus 1 is a split. So it's basically the different ways I can organize this. I can organize the sigma mi's to give the different permutations.
That also stand for the energy levels.
The sigma mi.
I mean, it has the.
It basically is basically related to the number of energy levels that there are. Okay. So what about that? If I ask you to do the boron, well, what do you want to do, the hydrogen or the boron?
Both.
Both. What do you want to do first?
Boron.
Boron. You know how to choose your battles. Boron. So boron is coupled to what? To hydrogens. And we are assuming that the borons cannot couple to each other, which they could. But let's assume that they can to make it simple. So how many different borons there are? One. So there are two borons, but they are equivalent, right? They're equivalent borons. How many hydrogens I have? How many different kinds of hydrogens I have? One. Right? So the boron, we have NMR will be what? Well, the signal of boron, which is just one boron, and it would be split by hydrogen. So
Do we ignore the hydrogens that would be with the R group because
these R groups are quaternary carbons. Quaternary carbons.
okay.
Yeah, I said that they were quaternary carbons specifically so you don't have problems there. So I have two hydrogens. I fill the field for those two hydrogens, and my splitting is going to be what? 2 times 1/2 times 2 plus 1, which is equal to 3.
Yes.
But since what is splitting me is a atom with a spin of 1/2, I can use Pascal triangle, and then my boron NMR signal right?
Yes.
Are you with me?
Yes.
Because you're not gonna like the proton signal.
They're bonus, right?
Wait, why is the I?
What?
Why is the I transfer the I is true?
The I is the splitting, so is of the atom that is split. So it is hydrogen. So that's the splitting formula. So it's for the atom that is split. All right. So boron. So hydrogen NMR. What is my problem now? My problem now is that I have a proton NMR, and now I have two boron atoms that are going to split the signal of those protons. Right? What happened now is that I would love to tell you that you can use the Pascal triangle, but you can't. Why?
The spin is 3/2.
Because the spin is 3/2 and you cannot use Pascal triangle for anything that is larger than 1/2. So you can use the splitting formula if you want.
Is there another triangle?
There's no other triangle.
Is there a square?
There's no square.
Draw this.
You can use the splitting formula if you want to get scared at the beginning. So that would be what?
4.
At least you know that your splitting will be 7. Is that the hard part? Just look.
That was the lowest point.
You know, it's that side, your order book just have an 8.
This is a Thursday night syndrome. Alright, so there are different ways of doing this. So basically, you have 2 boron atoms. The first case that you can have is that you can have the 2 spins having both oriented towards the field with 3 halves, right? The sigma mi is going to be what? 3? So how many ways I have that my sigma mi is 3? 1. The other case that you can have is that you can have 1 still have 3 half, so the other 1 half. Then your sigma mi is going to be 2. And how many ways? Yes, 2 ways. But of course, you can keep going, and the other thing that you can have is 1 half and 1 half. You have to keep your sigma mi going from top to bottom, right? So then what? How many ways that your sigma mi is 1? No. There's 2.
Because there's 3 halves.
There are 3 ways, right? 3 ways that your sigma mi is 1, because it can be this, but it can also be 3 half minus 1 half, and of course the inverse of this. So that makes it 3 ways. Are you with me?
Yes.
So then the rest is just keep going. So minus 3 halves and 3 halves will give you a sigma mi of 0, right? How many ways?
4 ways.
4 ways.
And then, can we assume it's symmetrical? And then it's going to repeat now? Or can we not do that?
It's going to repeat.
So there is a triangle.
Yeah, but if you do it with something of 5 halves, you will remember that it will not give you the same thing. But with 3 halves, okay, and if there are 2, all right, you ruined it. Anyway, so in order to have sigma mi of minus 1, minus 2, and minus 3, then my counting will be minus 1 half, minus 1 half, and of course there's 3 ways of doing this as well, because you can have the minus 3 half, 1 half, and the inverse, and then for minus 2, I can have minus 3 halves, 1 half, and there are 2 ways of doing that. And for the minus 3, it has to be minus 3 halves, minus 3 halves. So in any case, there's just 1 way of doing that. So your proton NMR for this system is going to be one, two, three, four, three, two, one.
Hey, I honestly don't get why, let's just say 1 half and 1 half. How do you get to 3 ways again? You were talking with some kind of inverse,
3
but I
ways?
kind of missed the boat right there.
Okay, you can have these 2 spins. There's only 1 way of having these 2 spins. If you invert them, it's exactly the same. But these 2, you can have 3 half, 1 half, or you can have minus 1 half, 3 halves. that means that either this is 3/2 and this is minus 1/2, or this is 3/2 and this is minus 1/2. They're different. So you have two ways in which you can do this. These two ways, and this that is the same. Then three ways. Three ways in which the sum of mi's minus 1/2 minus 1/2 is 1. 3/2 minus 1/2 is 1.
Oh.
Minus 1/2 plus 3/2 is 1.
Okay.
Three ways in which your combinations can be.
Okay.
My question, so I mean, I think this is the hydrogen is basically the bromine, so why we have the 1/2, but no, I mean, why we have the 1/2 for the
Because the mi numbers can be I minus 1, I minus 2 minus I. So that means that my mi's are 3/2 minus 1/2 minus 1/2 and minus 3/2.
Right? So we can just take any number from.
Questions? More questions? Good? Really?
I minus 2. Does it go to I minus 3?
It goes as much as you need, so it goes to minus I.
Okay.
So if my I is 3, for example, it will go from 3 to minus 3 in intervals of 1. 3, 2, 1, 0, minus 1, minus 2.
So what's the change in variables?
The change in MI,
I'm sorry, the sigma. What does it represent?
it represents the number of energy levels. So this represents that you can have you can have two spins oriented in the same direction. So it represents the total momentum of the dynamo.
And each momentum is a different angle.
Each momentum is a different energy because when you have 2 3/2 oriented with the magnetic field, the total magnetic field that fill the hydrogens is stronger because you have the sum of the two borons plus the magnetic field of the instrument. When you have that magnetic field reduced to 1/2, then the magnetic field that the hydrogens feel is strong, but not as strong as this. So it is 2. It is strong, but not as strong. And then you get to 0, in which they don't feel any field, just the field of the instrument. And then they start feeling less field because then now the spins are pointing in the other direction. So it represents the total magnetic moment contribution from the spins.
So when we are essentially like plotting the spin, like we have to basically draw the spinning arm. So on the axis, are we basically putting down how many ways that was like what's on the axis?
In the axis.
Yeah, on the
I'm just saying the contribution. So the signal, it would be 4 times this, 4 times this. This is 1. This would be twice as big. This would be 3 times as big. It would be 4 times as big.
So each time, so basically each of the contributions is the energy level or how many ways you can have.
How many ways you can have? Because basically what you're counting is the number of microstates in which you can have. So the number of ways that this can be organized. So there's only a way that you can have 3/2 spins, but there are 4 ways in which you can have 0 spins. So since this is random by probability, you will have 4 more times 0.
And for the energy levels here, is that true that the energy gap between the continuous energy levels are the same, right? For example, from the 3 to 2 and from the
No.
2 to 1, that's
No. The energy levels are changing. That's why we have the splitting. Each one of these lines have a different energy.
yes, but the gap.
The gap is changing.
Oh, the gap is also changing.
If the gap doesn't change, the energy doesn't change.
I mean, the gap can be constant, and the energy is still,
No.
I mean, 4, 3, 2,
The
1.
gap is constant for 1 atom.
Uh-huh.
But here we have 5 different combinations. So you could say that an atom that have this configuration and a molecule that have this configuration is different than a molecule that have minus one half configuration.
Yeah.
They are magnetically, they are different molecules. So for this combination, the gap is the same, but it's different than the gap from this combination, or for any of these combinations.
All right.
Questions? Yes.
So how would our analysis of this changed if it had been diborane instead of with the carbons? Like,
With hydrogen,
yeah,
with other hydrogen.
with other hydrogens.
You tell me.
I guess my main question is then do you just like use more hydrogens for that equation to get the splitting and then use the same triangle? And then does it change anything with the protein?
Well, you have to remember that the splitting formula works for the same kind of hydrogen. But is that kind of hydrogen the same kind of hydrogen? So then you will have a second splitting that you will have to calculate. Right?
Like 2 separate problems.
You have 2 separate problems. You first solve one and then you solve the other. That's basically the way it works. Yeah, I didn't want to go that way because the spectrum will be a mess if you start splitting that. But I mean that is basically the way you solve one and then you solve the other. Other questions?
So when we are doing the listing of the spin numbers, essentially, so first of all, we pick the atom that's splitting into 1 hydrogen.
Yes.
And we also, like, they're like, for example, here we have 2. Let's say we had like 3 hydrogens in which are going to put up 2.
If we have
We have like the 2 bonds connected to 2 hydrogens. Just that's just it. Then you would have 3 of those.
if you have 3 bonds with 2 hydrogens,
No, sorry, you have the 2 bonds.
the 2 bonds.
And in between the 2 hydrogens, you have 1 more, right?
One more hydrogen.
Yeah, so you will have 3 of those.
Can I have others in there?
So when you're doing the listing, you will have 3 rows and then you do it. Right.
If I have an extra hydrogen there, what spectrum we are? Boron or hydrogen?
The boron. I mean, basically what we just did.
The same that we just did. Are the 3 hydrogens equivalent or not? Let's suppose that the 3 hydrogens are equivalent, like they are kind of like forming a triangle. Let's assume that they're equivalent. So if the 3 hydrogens are equivalent, how the spectrum is going to change?
You have 2 rows.
Huh?
Two more splits.
Huh?
Two more splits, because the number goes from 2 to 3.
How the proton NMR spectrum is going to change if I have one more hybrid? Let's do the splitting formula again. 2 times what? 3 halves times what? Times 2 plus 1. How is my proton NMR going to change? In no way. What is going to change? What it does going to change is what?
The boring NMR.
Nothing.
No?
No, in the proton NMR, nothing is going to change.
Yeah, but-
Where I going to have a change?
For the boring NMR.
In the boron NMR. In the boron NMR, then I'm going to have what?
Yes.
I will have a 1, 3, 2. Yes?
Does the magnitude of the heights change as a function of the number of protons that you have?
Here?
Yeah. Or
But-
does it just matter that the relationship?
It doesn't really matter.
Okay.
Well,
I
well, if I have, you're talking about if I have other protons. If I have 2 other protons that have other splitting around here, then this will be 3 times as this. Is that what you mean?
Yeah.
It will be more intense because I have more protons, the intensity. But the splitting
It's the same.
will be exactly the same.
So if we have the one extra hydrogen between the boron, so what does the formula mean? It will be 2 times still 1/2.
I'm sorry.
Oh,
What will change?
so the formula.
The formula? The formula will just change here. Instead of 2, I have 3. So that will be 4. And how many I have in my Pascal triangle here?
4.
131.